definition of one-to-one function. Well, suppose you have a function like f. Let f maps set x into set y. We say that this function is one-to-one. So we write it as 1-to-1. Instead of just keep writing 1-to-1, you write it as 1-to-1. If, well, here we have if f of x sub 1 is equal to f of x sub 2, what's the meaning of that? It means that if y values are the same, so this is the meaning of that. If y values are the same, we can conclude that x values are the same as well. So if y values are the same, then x values are also the same. Okay, well, let us get back to previous chapters about P then Q. Recall that if you have P then Q, then the contrapositive of P then Q, if you have P then Q, the contrapositive says not Q, then not P. These two are the same. These two are equivalent to each other. Well, okay, what is the contrapositive here? If y values are the same, then x values are the same. X values are the same. Are the same. Okay, so the contrapositive says, hey, if x1 is not equal to x2, if x values are different from each other, then y values must be separated. F of x1 is different from f of x sub 2. So the contrapositive, x values are different. So as y values. Well, okay. Have I seen one-to-one functions before in calculus? Yes, you did. We had a test for that? Yes, you had. It was called horizontal line test. So recall that in calculus, we had this case. In calculus, we said, well, suppose you have this parabola like x squared. Is this a one-to-one function? No, it's not. It is a function, but it is not one-to-one. Why is that? Because it doesn't pass horizontal line test. Horizontal line test says, hey, any horizontal line cannot have more than one intersection with the graph. But horizontal line here has more than one intersection with the graph. Since it does not passes horizontal line test. Horizontal line test. So I expect you to ask, why do we even need one-to-one functions? We already have functions. What's the point of defining something new? One-to-one? Well, we're going to use one-to-one functions in composition between two functions. If a function is not one-to-one, you cannot define the inverse and eventually compose the function with its inverse. You don't get the identity function. So note that. Note that. We need one-to-one functions to define the inverse function. So, example for you. Which one is one-to-one? One-to-one. So the first one, this definition is just using finite sets. You have set A, the second set here, and you have function f that defines this way. This function says, hey, I maps A to W, then I map B to V, B to V, then I map C to X, C to X, and then I have D, which is mapped to Y, and you have U as well. So this is the first one, part A. This is your function f. So function B says, here you're defining a function like function G, which behaves like this. So you have A, B, C, and D. Well, function G maps A to W, C to W as well. And then this guy takes B to U. Then this guy takes D to Y. You have X and you have your V here. C. This function is defined this way. It says, well, I have f of x equals to four x minus 1 f from R real line to real line. It takes x, each element in R, and it gives you 4x minus 1. And the other guy, D, you have function G from N natural set to natural. Okay, this is interesting. It takes N and it maps it to N squared. Very well. So is this guy one-to-one? So take a look at the definition. If y values are the same, x values must be the same. Do you have equal y values? No. So since y values are not equal to each other, we're not worried about anything. To each x, you have specifically 1y. So this is an example of a one-to-one function. What about this guy? It says, hey, you have w here, which is connected to two x values, but these two x values are not the same. Or you have x1, which is different from x2. x1 is different from x2. x1 is A, x2 is C. They are not equal to each other, but their y value is the same. Well, g of x1 is w, which is the same as g of x2. So it is not one-to-one. What about this guy? Okay, this is just a line in xy plane. It passes horizontal line test. This is just a nice line. It's a line in xy plane. It passes horizontal line test. Just one intersection. Horizontal line test is passed. So it means that they have a one-to-one function. What about this guy? Just be careful about the domain of this function. It says it is n. So your x value, your input values, they are not negative. So since you don't have negative, you don't go to the left-hand side of the graph. So the graph of this guy is like this. If you want to graph it, you have, well, if I plug in 1, I get 1 and 1, 2 and 4, and so on. So let's just graph it a little bit here better so you can see. Does it pass horizontal line test? Of course. So it is another example of a one-to-one function. But what if I change the domain to z? I'm going to write these side by side so you see the difference between them. If I define function g from n to n that maps n into n squared, but if I define another function like h from z to z that maps n to n squared, this guy is one-to-one, this guy is not one-to-one. So this is a one-to-one function. This guy is not a one-to-one function. Take a look at the graph. This function g, it doesn't take on any negative value. It starts from 1 because my domain is n. So you get 1 and 1, 2 and 4, and so on. It passes horizontal line test. Any horizontal line has at most one intersection with the graph. But what about this guy? This can take on negative and positive values. So if you take a look at the graph here, the graph of function h, it takes on negative and positive values on the horizontal axis. So 0 and 0, 1 and 1, negative 1 and 1, 2 and 4, negative 2 and 4, and so on. So as you can see, you have two dots on the same horizontal line. Unfortunately, it doesn't pass horizontal line test. Horizontal line test is not pass. That's why it's not a one-to-one function. So far we talked about one-to-one function. Now we're going to talk about surjective or unto function. So before writing the definition, tell me what is the difference between these two functions. Question. What is the difference between these two functions? The first function says, hey, you have f of x equals to 4x minus 1, and function f takes r, it maps it to r, and it has a nice definition, f of x is equal to 4x minus 1. The second function, f, takes n to n, and f of n is defined as 4n minus 1. Other than the fact that we know these two have discrete, one of them has discrete graph, the other one has the continuous graph. What other differences you see between these two functions? What if I just change the range and domain into z? Let's just write it in much more broader range that you can see, hey, it takes some negative values and positive values. So we know that the graph of this one is discrete, the graph of this one is continuous, other than this. In the sense that you're taking a look at the codomain, right? You're taking a look at the codomain. What is the difference between the codomain of these two functions? And how does the codomain affect the function itself? So can I use any y value here? Can I take any value from z and use f of n as that number? So for example, can I take 3? Can y be 3? Can I just randomly select something from the codomain and then say, hey, y or the output value can be 3? Okay, now I have to think about it. If y value is equal to 3, it means that for n, it means that for n minus 1 can be equal to 3. So it means that 4n is equal to 4 and n is equal to 1. Okay, remember that n is coming from z. So since 1 belongs to z, I'm happy about it. I don't have any problem. Well, now, can y be equal to, let's say 0, 1, something else? Can y be equal to, let's say 1? So what's the meaning of that? If y is equal to 1, it means that this expression is equal to 1. So it means that for n minus 1 is equal to 1, for n is equal to 2, and n is equal to 2/4 or a half. Okay. N coming from z, can it be a fraction? Of course not. So now you have to think about this. I have a function that I'm not allowed to take every value from the codomain and plug that in for my y. For this function, you don't have any problem with that. Take any random r real numbers, you can easily solve for x. So if y is equal to 4x minus 1, then 4x is equal to y plus 1, or x is equal to y plus 1 divided by 4, which is, of course, a real number. I don't have any problem with that. I'm dealing with R, and every type of function, every type of number here is acceptable. So we say that this function is onto, this function is not onto. This is onto or surjective. This function, this is not onto or it's not surjective. So as you guessed, it has to do with y values in the codomain. We say that, well, a function like f, let me leave this example here for you, definition of onto function. Function f that maps x into y is called onto or surjective if for any y value, for any y in the codomain, there is an x in the domain such that f of x is equal to y. For any y value in the codomain, you can find an x in the domain. This x is acceptable, this x is not acceptable because it doesn't belong to z. That's why this function is not onto. One and onto function. So definition of bijective function. So we say that a function like f, function like f that maps x into y is called bijective, or sometimes they call it one-to-one correspondence if f is one-to-one and onto. Just a quick example. In calculus, you learn f that maps R to R, and as a real line, x goes to 4x minus 1. This guy is one-to-one. This function is one-to-one, and since for every y in R, y is equal to 4x minus 1. X can be related to y, 4x is y plus 1, and x is equal to y. X is equal to y plus 1 divided by 4 belongs to R. It is onto as well. So you have a one-to-one and onto function. So this is a bijective function. So example, so remember in calculus, you learned about logarithmic functions. Okay, but where they are coming from? Logarithmic functions. What's the origin of logarithmic functions? Well, remember that we start talking about functions in calculus, in algebra. Basically, we talked about linear functions, quadratic functions, cubic functions, radical functions, rational functions. Then we talked about exponential function. Let y equals to a to the x be an exponential function. Exponential function. Well, so if a is greater than 1, the function is an increasing function. Suppose we are working with an increasing function here, a to the x. A to the x. Well, my question is this function a one-to-one function? Is a to the x a one-to-one function? Okay, check horizontal line test. Horizontal line test says, hey, if any horizontal line has at most one intersection with the graph, we say that we have a horizontal line test passing for this function, horizontal line test, and we have a one-to-one function. So the answer is yes. So what's the use of a one-to-one function? It means that we can define the inverse of this function. Since y equals to a to the x is a one-to-one, we can define the inverse of this function. Okay. But how do we define the inverse? Remember that the inverse of the function is mirror image with respect to the line y equals to x. So this is the line y equals to x. The mirror image of this function with respect to this line is going to be like this. The inverse. So how do we represent the inverse of this function? The inverse of this function is actually called logarithmic function. This green graph is the graph of the inverse function that we write as log with base a of x. So this guy is log with base a of x, and it's the inverse of exponential function a to the x. So this example says, well, let function f we defined on the plane. So the domain is the Cartesian product between R and R, which is the plane. This is your domain. And it reduced 2 dimension into 1 dimension. No, it reduced this guy. It didn't reduce anything. So this is just R, Cartesian product with R. So we have another example about the reduction of the dimensions. So it just maps plane into plane. It takes X and Y from the plane, and it gives you another point, another ordered pair, X plus Y and X minus Y. So in this example, it says, hey, do we have a bijective function? Bijective function. Is this a bijection? Is it 1-to-1? Is it onto? 1-to-1, 1-to. Is this 1-to-1? So remember the definition for being 1-to-1. They say that a function is 1-to-1 if y1s are equal to each other, then you can conclude that x1 are equal as well. So this is the definition of 1-to-1. So what are we going to do? We're going to take 2 y values. One of them is x plus y, x minus y. The other guy, so let us take 2 y values. One of them is x plus y, x minus y, and the other guy is u plus v, u minus v. So we're taking 2 y values, okay? And now we want to show that the x values are the same. What's the meaning of that? It means that x is equal to u, y is equal to v. Okay. But here you have 2 ordered pairs. The first coordinates must be the same. The y coordinates must be the same. So x coordinates and second coordinates. Okay, let us set them equal to each other. We get x plus y equals to u plus v, and x minus y equals to u minus v. So what do we have here? We have 2 equations with 1, 2, 3, 4 variables. So let's add these 2 together. Add them. If you add these 2, you get 2x plus 0 equals to 2u plus 0 divided by 2. X is equal to u. So far, I showed that x and u are the same. Well, how do I show that y and v are the same? Okay, it's not that hard. Here, if I subtract these 2, again, it's just x plus y equals to u plus v, and here you have x minus y equals to u minus v. If I multiply the second equation by negative sign, I get negative x plus y equals to negative u plus v. So here, again, if I add these 2, add them, what do we get? We get 0 to y equals to 0 to v. Well, it says y and v are the same. So I take 2 points, y values are the same. I just showed that x values are the same as well. So I just showed that x and y is equal to u and v. So is it one-to-one? Of course, I just proved this. Is it onto? Remember the definition of being onto? For any y in the codomain, we need to show that there is an x in the domain such that f of x is equal to y. Okay. For any y in the codomain, for any x plus y, x minus y belongs to the codomain, I need to show that there is x and y in the domain. There is. So this is my goal. There is x and y in the domain such that f of x and y is equal to x plus y and x minus y. Very well. So let u and v be an element in the codomain. In the codomain. So if u is equal to x plus y and v is equal to x minus y, it means that 2x is equal to u plus v, or x is u plus v divided by 2. I found my x, and y is equal to, let's see, let's do the subtraction here, u minus v divided by 2 is my y value. I found x and y that I was looking for. For any y value in the codomain, you need to be able to find x value in the domain such that you have this relation. This is the definition of onto. So let u and v be a random element in the codomain. This is a random element in the codomain. If you define x to be u plus v divided by 2 and y u minus v divided by 2, then you're done. Why is that? Because these two are in the form of a fraction and you're dealing with x and y in R. So you don't have any restriction on being a fraction, being negative, being positive, being zero. No restriction there. As long as you can define x and y, there exists x and y in the domain such that satisfies this relation, then we're done. They have onto function. So the function is one-to-one, it is onto, so it is a bijection. Yes. Okay, can you see why here? Let me just move this a little bit off. So here you have 2x equals to u plus v. So x is u plus v divided by 2, and y is u minus v.